Hey guys, I'm going to go over the study guide for you here for lessons 3 and 4, the combinations and permutations and the probability distribution tables study guide for that test that's coming up. So let me show you guys that and we'll get to it right here. So number 1, pretty straightforward kind of question. Danny has 19 different flowers to choose from to make a bouquet. How many different ways can he choose 5 flowers? So pretty simple. We have 19 total. It's a combination kind of situation because he's just choosing a bunch of flowers from the selection. He's not arranging them yet in any way. He's just choosing the ones he's going to use. So we do that. 19 C5, 19 choose 5, and you should get 11,628, which is letter A. Okay. Number 2, in South Dakota, a license plate always consists of exactly 5 letters, followed by 2 numbers. The letters P, X, F, Q, and Z are never used. How many different license plates are possible? So let's illustrate our license plate here. 5 letters followed by 2 numbers. Just going to separate them there. So how many letter choices do we have each time we choose a letter? We have 26 letters in the alphabet minus 1, 2, 3, 4, 5 letters that we're never using. So that'd be 21 letters to choose from every time. And we can repeat letters because it doesn't say that we can't. So we're just going to have 21 times itself 5 times. 21 choices with each letter that we choose. And then with the numbers, we're choosing numbers from 0 to 9. Those are the digits that you would use on a license plate. And again, doesn't say that we can't repeat. So every time we have 10 choices. 0 is included. We have 10 choices every time. So when you multiply that all out, you should get letter C. Multiply this stuff together, and then you times that whole thing by this. And that's how you get this big, big, big number here. Okay. Debbie is watching a turtle race and wants to correctly predict the exact order of the turtles that will place first place and second place. If there are 12 turtles, what is the probability that Debbie will make her prediction correctly? All right, we know it's a permutation situation involved because the order matters, right? We have a race, and we're talking about first place and second place. So that depends entirely on the order, right? It's an order-related kind of concept. We're 12 total, and we have 2 positions here involved that we're choosing basically random turtles and putting them in these spots in the right order. So if you do that, 12P2, you should get 132. And now it wants a probability that she will make her prediction correctly. So her correct prediction would just be one choice out of the total 132 possible arrangements of these 2 first place and second place turtles out of the 12 turtles. So you pick letter C. All right. A computer has a password that consists of exactly 5 letters. And it says no letters repeated. I'm going to cross that out and say that we can repeat letters. I was a little tired when I typed this up, so I actually don't want that in there. So we are allowed to repeat letters now. What is the probability that a person could guess the correct password with one try? So 5 letters. I'm going to set this up a similar way, illustration-wise, from previous question. It doesn't say we're excluding any letters. So every time we just have 26 choices, or 26 letters in the alphabet. So each time we choose a letter randomly for this password, we're going to have 26 choices. And fortunately, we don't have to actually multiply this together because if you look at the answer choices, it's looking for a probability that a person could guess the correct password with one try. So that would be one possible password out of the total 26 times itself 5 times. I'm just going to write 26 to the 5th. That's the same thing as letter C. 26 5 times. An empty parking garage has 30 spaces, all of which are visibly numbered. If Calvin randomly chooses a parking spot, what is the probability that it will be a number greater than 13? All right, this is pretty straightforward. We know that there are 17 parking spaces with numbers greater than 13. So we just write the total number of spaces and the number that we want, and that would be 17 out of 30, which is letter B. Fairly simple. The combination on a lock contains 4 digits from 0 to 9. No number can be repeated. How many different codes are possible? All right. Again, draw our little lines here, our 4 numbers in our code. Numbers 0 to 9, so there are 10 choices, at least for the first time we pick a number anyway. But because we can't repeat whatever number we picked the first time, when we go to pick the second number randomly, we only have 9 choices. And then for the third number, we only have 8 choices. And then we lose another choice for the last selection here. So we multiply all that together because we can't repeat, and you should get 5,040, which is letter A. Open-ended, everybody's favorite. Let's read this and make sure we highlight. Always a best practice to highlight the important information here. A company did a survey of 100 of their employees. Get that total number, it's important. Of the employees surveyed, 50 were female, also important information. They asked the employees if they prefer to come in to work earlier than 7 a.m., represented by an E in the table, at 7 a.m., represented by A in the table, or later than 7 a.m., represented by L in the table. From the survey, a company found that the probability of randomly choosing an employee that is both male and prefers to come into work earlier than 7 a.m. is 0.10, hence the male and the E kind of intersecting there at the 0.10. The probability of randomly choosing an employee that is both female and prefers to come into work at 7 a.m. is 0.11, hence female A at 7 a.m. 0.11. And the probability of randomly choosing an employee that prefers to come into work at 7 a.m. is 0.38. So there's a male and female. The total probability is 0.38. They also know that of the employees surveyed, 25 of them prefer to come into work earlier than 7 a.m. So let's highlight that. That's important. The other stuff in here is important too, but they already took the liberty of putting that in the table for us. So we don't really need to worry about that too terribly much. So a goal here is to fill in the table with these numbers in this little answer bank here. So let's use some logic to do that. We know that the total probability of males and females that like to come into work at 7 a.m. is 0.38. And the females are 0.11. So if we do 0.38 minus 0.11, we should get the probability of just the males, right? Because these two need to add up to that one. So that would be 0.27. So we use that option. We're not going to use that again. They won't be repeated. 0.5 is occurring twice because we do need to use that 2 times in the table. And let's do that one right now, actually. It says up here, 100 employees total, 50 were female, so that means 50 were male. So this far right-hand column is the total men, right? The early at 7, later than 7, all adding up to the total amount of men. We have basically a 50-50 split, 50 men, 50 women. So the probability of randomly choosing a man would be the same as the probability of choosing a woman in this situation. So we can put the 0.5s over there. Okay, and then let's check out this last bit here that I highlighted. 25 of them prefer to come into work earlier than 7 a.m. So that means that 25 people out of 100 total prefer to come in at 7 a.m. Or I'm sorry, earlier than 7 a.m. So that would be a 0.25 chance that any person prefers to come in, whether it's male or female, earlier than 7 a.m. So now we have that. Cross that off, that counts. And again, just like we did the A column, for the E column, we know 0.1 plus whatever's in here needs to equal 0.25. So that means this has to be 0.15. All right. So now we can just say, because we're basically doing the same thing we did for the E and the A, knowing what things need to add up to and then filling in the blank, we're doing this horizontally instead. So I have 0.1 plus 0.27 plus whatever's in here needs to add up to 0.5. So that would be 0.37 there. So I'll make a little note there. That's 0.37. So then the difference here would be from 0.37 to 0.5 would be 0.13. So I can cross that off. Over here, I have 0.15 and 0.11. So that total would be 0.26. The difference between 0.26 and 0.5 would be 0.24. And then to get this final entry, I simply add 0.13 plus 0.24 and get 0.37. And I have now officially and effectively used all of the choices in the answer bank and filled this table. So please make sure you can repeat this process with different numbers on the test using all the knowledge that you get from the table, this first bit and this last bit, and your logic of how probabilities need to work. You have to have certain things adding up to other numbers in here. The ones that are labeled as total need to be the sum of the things being considered in these categories. And the open-ended, questions B and C are not related to the table, so we don't need to really look at that anymore. We'll just focus on this. In how many ways can you choose 8 shirts from a collection of 22 different shirts? So we're not arranging them. We're not choosing them in a particular order. We're just choosing just a handful of shirts, 8 shirts from our collection of 22. So we can just use a combination formula for that instead of permutation. And you get your 22C8, and that should give you, make sure I get this right, 319,770. So 319,770 different ways you could choose. My 7's a little sloppy. Different ways you could choose 8 shirts from a collection of 22. Lastly, once I've chosen 8 shirts, and how many different orders can I arrange them? Now we're talking permutation, and we have our total. Our total equals 8 shirts, and we are arranging 8 shirts. All of them. That wasn't very good. Let's try that again. All of them. So that makes it easy. We just do 8 factorial. We can crunch that number and get 40,320 as our response. And that is it. That is the whole study guide. So I hope you gained a lot from this. Keep watching this until you understand it. If you still need help, obviously, come and talk to me, or whatever you need to do, and we'll hope for a very successful test on this stuff. All right, thanks guys. Good luck on the test.